This is the walkthrough of the June 2010 F325 OCR paper. Question 1 is a fairly standard Born-Haber cycle question. If we look at the table of data, we can see that because we've got things like electron affinities and ionization energies, this is going to be our standard Born-Haber cycle, not the one involving enthalpy of solution. If we go on to the next page where the question is, and we can see it's fairly nice because we've got a Born-Haber cycle already drawn, and all we need to do is label the various steps. So if we start off going around and just labeling before we actually do the question, so we can see here, we start at the bottom, we've got elements forming a solid, so this is the enthalpy of formation of magnesium chloride. In this step, the chlorine stays the same, but the magnesium turns from being a solid into being a gas, so this is the enthalpy of atomization of magnesium. In the next step, we can see that the chlorine changes this time because the magnesium stays the same, but we've got Cl2 molecules splitting into two Cl atoms, so this is the enthalpy of atomization of chlorine. On this next arrow, chlorine stays the same, but the magnesium turns from being Mg gas into Mg plus and an electron. So this is the first ionization energy of magnesium. That is a 1. Final arrow on this side, we've got Mg plus turning into Mg2 plus and an extra electron, so this is IE2 for magnesium. And then finally, we've got gaseous atoms forming an ionic solid, so this is the lattice enthalpy for magnesium chloride. If you go back onto the previous page, then you will find the corresponding letters are from the top F, B, E, D and G. Okay, now just to help me with this next step, and this might be a good idea for you to do as well in an exam, I'm going to write the numbers in that go with all of these. So formation was minus 642 plus 76 for the atomization of magnesium plus 150. Now also, when I'm writing these numbers in, I need to think about the fact that there are two chlorines in this, so this number is going to be times by 2. Next one is plus 736, carrying on up, plus 1450. Electron affinity of chlorine, so this is a number that's to do with chlorine, so again this is going to be times by 2, and then this is the one that we want. So if we go on to that calculation at the bottom, this is the arrow that we're missing, the lattice enthalpy. It's pointing down, so we're going to go anti-clockwise around this cycle. So we're going to have 2 lots of 349, and then obviously if you go against the arrow, so you can see that this arrow is pointing upwards, but because I'm going anti-clockwise, I'm going against it, I'm going to reverse the sign and make it minus. And that applies to most of the arrows on this side. And then when I get to the enthalpy of formation, I can see that this arrow is pointing down. I'm following that arrow, so I keep the sign. Type all that in, and I get my final answer as minus 2,506 kilojoules per mole. It's 1 for showing your working and 1 for your final answer. If we move on to the final part of this question, so we can see that we're comparing magnesium chloride with sodium chloride. So what we're really looking at is comparing Mg2 plus with Na plus. So we're going to use the same thing we always use for these questions, which is CRAS. So that's charge, radius, attraction and size of enthalpy. Okay, so if we look at how we're actually going to answer this question then. So we're going to start off by saying that Mg2 plus has a greater charge than Na plus. Okay, now I always talk about this. It's very important that you either say Mg2 plus and Na plus, or that you say the magnesium ion and the sodium ion. If you're talking about atoms, then you are going to lose the mark. The next thing then that we're going to say is that Mg2 plus is smaller. Okay, so, or you can say smaller ionic radius. The key thing here is, in the mark scheme, you can get away with just saying that it's smaller. It's true that it's got a smaller ionic radius, but if you say atomic radius, then that mark will be taken away. And the final mark then, there will be greater attraction between Mg2 plus and the chloride ion. And that's the 3 marks that we need to answer this question. Question 2 on this F325 paper is a redox question. And it starts out quite nicely, or it looks like it's quite nice, with a balancing equation question. So what most people will do here is they'll start with the bromines. There's 2 on the left, 2 on the right. Oxygens, 3 on the left, make 3 waters. And then that leaves us with our hydrogens, so we make 6 H pluses. And many people will now move on to the next question and totally miss this mark. Now the reason is, because this is a redox reaction, we have to look at the charges. So if we look on the left hand side, on the reactant side, we've got 2 minus charges and 6 pluses, giving us an overall charge of +4. Whereas on the product side, we've got neutral species and an overall 0 charge. So clearly there's something wrong, because we can't have an imbalance in the charges. So we're going to start this again, and we're going to use the redox balancing method. So we're going to start off by putting the oxidation states on. So Br2 is 0, that's -1, and this is +5, which you can see from the Roman numeral up there. So if we look at what's happening to these bromine species, so this bromine species is changing by 1 electron, and this bromine species is changing by 5 electrons. Now the key thing with balancing a redox reaction is you need to make those 2 numbers the same. So all I'm going to do is I'm going to times this species by 5. I'm going to put a big 5 in front of that Br minus. Once I've sorted out the bromine, because that's the species that's been oxidised and reduced, I can go back to normal balancing methods, and it'll work really nicely now. So on this side I've now got 6 bromines, that means 3 Br2s, 3 oxygens gives us 3 waters, and then we're going to need 6 H pluses. So it's very similar to the original balancing, but we've now taken care of the charges, because if we look, we've got 1 minus plus another 5, so that's 5 minuses, 6 pluses, overall 0. On the right hand side we've still got neutral species, so it's still an overall charge of 0. Part B of question 2 moves on to the rates part of this question, and we can see that we're starting off with a rate concentration graph for the bromate 5 ion. It's surprising how many people will look at this question, ignore the graph, and move straight on down to the table of initial rates data. It's really crucial that you don't do that, because if you do that you won't get the order for the bromate ion. So I'm just going to annotate this as I'm reading through the question. So if I'm looking at this graph, I can see it's a rate concentration graph. I've got a straight line passing through the origin, which means that bromate is going to be first order, and I'll come back to that later. Carrying on to this table, so I'm looking at, I can see that the bromate ion is constant throughout, and that's fine because I've got the order from this graph up here. So I'm going to look at the bromide and the H plus ions. So between the first and second experiments, I can see that bromide doubles and the H plus stays the same, and the rate also doubles. So that means that the bromide is first order. Looking at the H plus then, So really I want two reactions where the bromide stays the same and the H plus changes. So that's going to be experiments 1 and 3 because that's staying the same but the H plus is doubling. Okay, so those are the two experiments that I'm going to pick, and if I look at what's happening to the rate, I can see that the rate increases by 4. So that means that H plus is second order. Now I'm going to move on to look at what the question actually wants me to do. Okay, so the key thing there is just annotating as you're going through this so that it's easy to look back and answer the question. So again, bullet points tell us how to structure an answer. So we're going to start off with the first one. Using those results, we're going to draw conclusions about the kinetics of this reaction. That really relates to orders. Okay? So, if we look at how we're going to structure what we say, we'll start off with the graph for the bromate ions. So, order with respect to the bromate ions is first because the graph is a straight line passing through 0, 0, or the origin. Okay, and we need to say all of that to get the first mark. Next thing that we're going to say is that between experiments 1 and 2, the concentration of bromide ions doubles and the rate also doubles. So the order with respect to concentration of bromide ions is first. Next one, between experiments 1 and 3, the concentration of H plus ions doubles and the rate increases by 4. So the order with respect to concentration of H plus ions is second. Okay, so now we'll stop and look at the marks. First mark comes for saying all of this first sentence, so identifying that it's first and explaining why. Second statement gets us 2 because we get 1 for identifying that it's first order, and we get 1 for our explanation, so Br minus doubles and the rate doubles gets us that second mark. And the third statement, similarly, 1 for identifying that H plus is second order, and 1 for our explanation, so when H plus concentration doubles, the rate increases by 4. Okay, so now we've done that first bullet point. Now we're on to calculate the rate constant. So the first thing we're going to need to do is to write a rate equation. So they always start the same way, rate equals K. We know that BrO3 minus was first order. Common mistake here is to miss that out, either because you missed the graph or just because you forgot it wasn't in the table. The Br minus was also first, but the H plus was second, so that gets squared, and we get a mark for writing that rate equation. Next, we're going to rearrange to get the rate constant. Okay, and it's a fairly simple rearrangement. And then we're going to substitute in the numbers. Now the easiest row in the table to pick is just the first row. So if you were to put all those numbers in, then you would get 1.19 times 10 to the minus 5 on top, and on the bottom 5 times 10 to the minus 2 times 1.5 times 10 to the minus 1 times 3.1 times 10 to the minus 1, and that's got to be squared. Okay, 1 mark for either of those, either the rearrangement, if you only got that far, or for substituting your numbers in. And if you calculate that, you'll get 1.7 times 10 to the minus 2. 1 mark for your number, and then 1 for your unit. So you've got moles per decimetre per second on the top, and we've got 4 lots of moles per decimetre on the bottom, because don't forget this one's squared. Okay, so only one of them will cancel, and that gives us 3 lots of moles on the bottom, so moles to minus 3, 3 lots of dm, so that's going to be to the power 9, and then we've got seconds to the minus 1, and it's 1 for the units. So that gives us 4 in the calculation section, and then we've got 5 for our explanation. So we've now done both bullet points, and that gives us a total of 9. Question 3 is an acids question. At the top we've got a paragraph that doesn't really tell us anything that we need to know to answer the question, so we're going to move on down. So we've got a series of experiments with acids and alkalis, and we're using propanoic acid, which is a naturally occurring weak acid. So again, bullet points tell us how to structure the answer, so we're going to start off with the first one. How could you prove that propanoic acid is a weak acid? So measure the pH. It will be approximately pH 3. Okay, so if you look at the mark scheme, if you quote a number that's greater than 1 and obviously less than 7, then you've got that mark. So we've dealt with that. How would you prove that it's a weak acid? You'd measure the pH and it'd be somewhere around about 3. Then how would you calculate the acid dissociation constant for propanoic acid? So 1, calculate H+, concentration of H+, using H+ equals 10 to the minus pH. Okay, so in this first step you said that you're going to measure the pH, and then we're going to say what we're going to do with it. So we're going to convert it into concentration of H+. So 1 mark for that up there, and 1 mark for doing this. Then we're going to write Ka expression, and because we know we're using propanoic acid, we're going to use the correct formulae in this Ka expression. Okay, so that would be our Ka expression, and for that we should get another mark, and we should also make note of the fact that because it's a weak acid we can use H+ squared over propanoic acid. And our final step then is we can substitute in the numbers, so Ka equals H+ squared, and obviously we've got H+ from up here, over 0.1, and I've taken that concentration from here in the question, and that's the 4th mark. So running through those again then. First bullet point, how would we prove it's a weak acid? We'd measure the pH and it'd have a pH in the region of a weak acid. Second bullet point, how would you calculate Ka? So you'd have to calculate the H+ concentration using 10 to the minus pH. Then you'd write a Ka expression, and then you'd substitute in the numbers. So you'd substitute in your H+ from step 2 here, and you'd substitute in the concentration of the acid from up here. Part B of this question. So we've got pH solution of sodium hydroxide, so that means that we're going to be doing Kw. And we've got a pH of 13.46, so that means that we're going to be using 10 to the minus pH. Okay, so again, get into the habit of recognising which calculations you're using as you're going along. So if we start off with this and we do 10 to the minus 13.46, 0.46, and that's going to give us 3.47 times 10 to the minus 14 moles per decimetre of H+, and that is our first mark. And then the second thing we're going to do is we're going to rearrange the Kw expression to give us OH-, which of course will be the concentration of sodium hydroxide because we've got one OH- ion in it. So we're going to have Kw divided by H+. Kw is the one number that, apart from Avogadro's constant, that's on your data sheet. So 1 times 10 to the minus 14 divided by 3.47 times 10 to the minus 14. And that gives us a final answer of 0.29 moles per decimetre. And that is the second and final mark. That is a 2 there, by the way. Okay, so 0.29 moles per decimetre. Question 3, part C, is a buffer question. It's asking us about the formation of a buffer made from propanoic acid and sodium hydroxide. So, key things in this question then are the bullet points. If you've watched our other video about buffer solutions, you may well want to start this answer by explaining what a buffer solution is. But if you look at the question, you can see that we're told that. So it says here the buffer solution contains an equilibrium system that minimises changes in pH when small amounts of acids or alkalis are added. So we don't really need to say that down in our answer. But we do need to deal with the bullet points. So we're going to start off with the first one here. So it says, explain why a buffer solution formed when an excess of propanoic acid was mixed with aqueous sodium hydroxide. So we'll start off by explaining how this buffer is formed. Okay, and for that we will need to write an equation. So we start off with our propanoic acid, and that's been reacted with sodium hydroxide, and what we will make from that is sodium propanoate and some water. Now we also need to explain why this is a buffer, because if you took some propanoic acid and sodium hydroxide in equal numbers of moles, then you would get a neutralization reaction and you'd end up with a neutral solution. This is not a neutral solution, this is a buffer, so that means that there will be some propanoic acid left. Okay, what we sometimes talk about is partial neutralization, but to get the mark on an exam, you really do need to talk about the fact that there will be some propanoic acid left at the end of this reaction. The next thing that we're going to write is the buffer equilibrium, or the buffer equation. So the system that exists in this buffer is propanoic acid and that will be in equilibrium with the propanoate ion, and some H+ ions. Okay, so apologies, that just needs a reversible arrow in there. Okay, so going through this first bullet point then, we've got why a buffer solution forms when an excess of propanoic acid is mixed with sodium hydroxide. So we've written an equation for that reaction happening. Then we've explained why that is a buffer by saying that there will be some acid left over, otherwise it would just be a neutralization reaction. And then we've given the equation for the buffer that we've made. Okay, so next thing, we can cross off that bullet point. The next thing is we go to the second bullet point, and we're going to explain how it works essentially, so how it controls pH. So we'll just leave that on screen so we can see what we said so far. I'm going to start off with the addition of acid. So if we were to add acid to the buffer solution, then we would essentially be adding H+ ions. If we look up at the
buffer equilibrium, then we can see that H plus ions here will react with the propanoate ion. Okay, so we can write that down into the equation that we were making there. And that will form propanoic acid, which means that equilibrium shifts to the left. Okay, so if we just talk through that again, we are adding extra H+, that's going to react with the propanoate ion and equilibrium is going to shift left. If you like to think in terms of Le Chatelier's principle, if we're increasing the concentration of this product, then to minimise that change, the equilibrium is going to shift left to reduce the concentration of the H+. Next thing we're going to deal with is the addition of alkali. Okay, so when we add an alkali, we are adding OH- ions. OH- ions will react with H+ ions, and they will form water. Okay, so once again, if we look up at the buffer equation, we can see that if we add OH- ions in, then it's these H pluses that are going to react. This time we are removing them because we're taking them away and making water. So if we are reducing the concentration of H+, then the buffer equilibrium is going to shift to the right to replace those H+ ions that we've just taken away. So we need to say equilibrium shifts to the right. Okay, so now we'll go through the marks again. We talked about the first bullet point. Now the second bullet point talked about explaining how the buffer solution controls the pH when an acid or an alkali is added. So we've talked about the addition of acid, and we've given an equation for what would happen, and we said which way the equilibrium shifts. That's 2 marks. Then we've talked about what happens when we add alkali, and we've written an equation, and we said which way the equilibrium shifts. And if you have to look back at that answer, you'll see that we have covered all 7 marks that you will always get for a buffer question like this. Part D brings us on to conjugate acid-base pairs. So if we look at what we've got nitric acid, which you should know is a strong acid, and we've got propanoic acid, which is obviously a weak acid. Remember, all carboxylic acids will be weak. Nitric acid is an acid that you should have learnt is a strong acid. That means that the nitric acid is going to behave as the acid, and because propanoic acid is weak, it's going to take on some basic behaviour. So let's just remove them. If we look at what's going to happen, nitric acid is behaving as the acid, therefore it will be a proton donor and it will turn into NO3- because it's lost its proton. So if this is acid 1, then this must be base 1, that's its pair. If nitric acid is going to be a proton donor, then propanoic acid must be the proton acceptor. So we're turning this into this protonated version over here. So this means that propanoic acid is acting as base 2, and on this side we've got its conjugate acid, which is A2. Now marks in this question, you've got 1 mark for getting the correct species on the right hand side of the equation, and you've got 1 mark for correctly labelling the acid-base pairs. Okay, so just bear in mind it wouldn't matter if you had gone for A2 and B2 and then B1 and A1 labelled that way around. The key thing with your labelling acid-base pairs is that you've got your A's and B's in the right places, and you're linking nitric acid with NO3- and propanoic acid with its conjugate acid on the right hand side. Carrying on down to part E. Okay, so we've got some really nice simple equations to write here, although it does get a little bit more complicated when you have to turn it into ionic, but we'll start off with the straightforward one. We've got magnesium reacting with propanoic acid. And we're going to make magnesium propanoate. So just remember that the propanoate ion, this would have a 1 minus charge. So because magnesium's in group 2, we're going to need 2 of those ions. And we are going to make H2. Remember, this is metal plus acid makes salt and hydrogen, so that's MASH from AS. Then we've got the ionic equation. So I'm going to do my rough working down here. We've got propanoic acid reacting with sodium carbonate. Okay, very important you're able to get your formulae correct. And we're going to make sodium propanoate and some CO2 and some water. Now let's balance it. So we're going to need 2 of these and 2 of these. Now the key thing with writing ionic equations, or one of the key things along the way, is that you get state symbols. So we see we've got aqueous propanoic acid. So let's put that in there. Aqueous sodium carbonate. I'll put that in there as well. We've got a salt over here. Remember, ionic salts generally soluble in water. Carbon dioxide is gas and water is a liquid. Next thing, anything that is aqueous in solution will turn into separate ions. So we're going to have 2 lots of the propanoate ion and 2H+. And then from the sodium carbonate we're going to have 2 sodium ions and a carbonate ion. On the right hand side we're still going to have propanoate ions, and there will be 2 of them, and 2 Na+. Remember that gases don't change because it's only the aqueous things that will change, so the CO2 will stay as it is, and the water will stay as it is as well because that's a liquid. Next step is to cancel, so we're going to get rid of the sodium ions because they're on both sides of this equation, and the propanoate ions, and what we're left with is 2H plus CO3, 2 minus, making CO2 and H2O. Okay, we've not been asked for state symbols, but sometimes you will be and you'll get an extra mark for it. But in this question, this is all that we're looking for. Question 4 is an electrode potential question. There is of course an introduction to this question which doesn't tell us anything we need for answering the actual questions here. So we're going to scroll straight down to this table of half cell equations with electrode potentials. And the question says an electrochemical cell can be made based on systems 2 and 4. Draw a labelled diagram to show this cell. Okay, so we're going to start off by looking at those 2 half equations and deciding on which type of half cell we're going to draw. So we're going to start off by looking at system 2, and we can see that we've got aqueous ions on both sides of that half equation. So the half cell that we're going to draw looks like this. We're going to use a platinum electrode, and that's because there's no solid ion in that half equation. In the solution we've got 1 mole per decimeter of iron 3+, and 1 mole per decimeter of iron 2+. Let's go back up and look at the silver one. So in the silver half cell we've got silver aqueous ions and silver solid, which means that we can use that solid silver as the electrode in this half cell. Okay, so there we've got a silver electrode, and that must be in contact with 1 mole per decimeter of silver ions. So far we've got 2 out of the 3 marks on this, 1 for each correct half cell, and then we're going to connect them together using a salt bridge, which must of course be labelled, and a voltmeter. Okay. Final thing to check is that you've not left any gaps in your circuit. So for example, your salt bridge extends all the way down into the solution like so, and it doesn't finish mid-air. And that's the third mark for your labelled salt bridge and voltmeter. Moving on to part 2, fairly standard question here, seen on a few papers, says state the charge carriers that transfer the current. So what's carrying the current through this wire? And the answer is of course electrons. And moving through the solution and of course the salt bridge, we have ions. Then for the overall cell equation, so you may want to refer back to the table if you've got a paper copy in front of you. And I'll just remind you the two half equations we were using was this one, and the potential was 0.77 volts, and we were using the silver half equation, which has a potential of 0.34 volts. So if we're going to combine two half cells, then the first thing to decide is which one is going forwards and which one's going backwards. So for this we look at the cell potential, so we can see that 0.77 is more positive than 0.34, so the iron half cell will proceed in the forwards direction and the silver half equation will proceed in the backwards direction. Now I always find it useful at this point to rewrite the one that's going backwards like that. Okay, so then it's a fairly straightforward thing to add them together, because we don't need to do any multiplication in this one because we've got one electron in the top half equation and one electron in the bottom. So all we need to do is add them and cancel those electrons out. And that's our 1 mark for the overall equation. Cell potential, so we should remember that E cell is equal to the positive terminal take away the negative terminal. So in this case it will be 0.77 take away 0.34, which would give us 0.43 volts. Question 4 part B is asking us to use the data in the table on the previous page to identify oxidizing and reducing species. Now this is typically something that students tend to find quite difficult, so we're going to look at this together. If we look back at the table, this is the data that this question is asking us to use. Now the first part of this question asks for a species which oxidizes Fe2+ to Fe3+. Okay, so we're looking for an oxidizing agent. Now, the key thing here is that oxidizing agents are found on the left. Okay, so when you get given these tables, you will always find oxidizing agents on this side, which means that the reducing agents are over here. Okay, and that's worthwhile bearing in mind. Now, if we look at what we've been asked to do, so we want something that's going to oxidize Fe2+ and turn it into Fe3+. So we want this half equation to proceed in the backwards direction. Now remember, when you've looked at electrode potentials in the past, whichever half equation has the least positive electrode potential is the one that will proceed in the backwards direction. So to send this half equation in the backwards direction, we need something that is more positive. And for that we have two choices. We have this one and this one. Both of these are in the mark scheme, so it doesn't matter which one you choose, but it does matter what you write down. So if you were to choose system 5, then what we would write for the answer is Cl2. Okay, the only thing we don't need to write down are the electrons. If, on the other hand, we were to choose system 6, then we would need to write down oxygen and H+, because again, we need to state everything that's on the left of this half equation, excluding those electrons. So we put those answers in just to remind ourselves. We can have Cl2 or O2 and H+. Now the next part of this question asks for something which will reduce Fe3+ to Fe2+. Let's deal with that first bit to start with. So we want a reducing agent, so we're looking for something that's on the right hand side of this table. And this time we want this half equation to proceed in the forwards direction because we want to reduce Fe3+ into Fe2+. So if we're asking for this half cell to be going forwards, then we need something that is less positive than that. So we've got the choice of this, or this, or this. Okay, so systems 3, 4, or 7. Let's carry on reading that question. Now it says it does not reduce Ag+ to Ag solid. So let's look back at this again. So we don't want this equation, the silver equation, to proceed in the forwards direction. We don't want that to happen. Okay, so essentially what we're saying is that we want this one to go backwards. If we want this half equation to go backwards, then we need something that's more positive than it. Okay, so if we look at what we're discounting now then, we're effectively saying that we're not considering system 4 because we're talking about the silver half equation in the question. And we've just said that we need something that is more positive than 0.34, so we're going to discount system 3, which leaves us only with the choice of system 7. Again, we were looking for the reducing species, as we talked about looking for the species that's on the right, which makes the species I-. Part C is a question about fuel cells. It's a very nice question for this part of the paper. Again, there's no real balancing of equations or anything like that on this. Most of these bullet points are things that you could just go away and learn off by heart. So, if we look at this question, it's a longer answer question, lots of lines, but again we're given bullet points, and remember that bullet points always tell you how to structure your answer. So we're going to start off with the first bullet point. Now what I always say here is that fuel cells require a constant supply of fuel. Okay, if you were to look at the mark scheme, you might be following us through with the mark scheme, and you'll see that that is here as an allowed answer. It's not the most common answer, but personally I always find this one slightly difficult to remember because it's quite wordy. So a fuel cell converts energy from reaction of a fuel with oxygen into a voltage. I think it's just easier to remember a fuel cell requires a constant supply of fuel. Carrying on down from that, so we've dealt with that first bullet point. The second bullet point asks for the equation for the overall reaction in a hydrogen fuel cell. So we've got hydrogen reacting with oxygen, making water. Two ways of balancing this. One is by adding a half there, or you could go for 2H2 plus O2 makes 2H2O. Either one is acceptable. So this is mark 1 and mark 2 in the mark scheme, and that's the second bullet point. Third bullet point, we've got storage of hydrogen. So make sure you show the examiner what you're talking about. And we've got three choices here. One, we can say storage as a liquid under pressure. We could say adsorbed within, adsorbed is adsorbed on a solid support or material. We could have absorbed onto a solid material, and the third and fourth marks are awarded for any two of these three. And the final marks, that's this bullet point, the final mark Why do some people consider using hydrogen as a fuel for cars consumes more energy than using fossil fuels? And that's because energy is used to make hydrogen. Okay, I generally tend to add on the end of this one, this energy is generated from fossil fuels. Okay, now that's not required on this mark scheme, but if you're going to train yourself to answer this question, this is a very good thing to tag on to the end, because sometimes the mark scheme does require you to make that realisation that the energy does come from fossil fuels. And that's the final bullet point and the final mark on this question. Question 5 is a KC equilibrium question. It's quite late on in this paper. Generally KC questions appear earlier in F325 papers, which kind of tells you a little bit about what the difficulty level of this one is going to be. So it starts off quite nicely with some fairly typical KC questions. So we're starting off with the Haber process. Again, the Haber process is a favourite for examiners. And we're asked to write a KC expression, which is very straightforward. So we've got products, and don't forget that the numbers in the equation become the powers in the KC expression. So again, 1 mark, very straightforward writing of the KC expression. Deducing the units, we've got 2 lots of moles per decimetre on the top, and on the bottom we've got 4. Okay, so then we can cancel 2 of those out, which leaves us with 2 on the bottom. So we're going to take them up to the top, and we're going to have moles to the minus 2, decimetres to the 6. The correct way around, of course, is the higher one first, but either will do. Okay, carrying on down. This is where it gets slightly trickier. So we've got some information about a research chemist carrying out the Haber process. The chemist is mixing together the nitrogen and hydrogen, and the total volume is 6 decimetres. Now remember, we tend to work in moles per decimetre, so we're going to need to sort that out first. Again, even though it's not got lines in this question, we can use the bullet points to try and tell us what we're doing. So the first one is to sort out this thing with the 6 decimetres. So if we've got the nitrogen and we've got 7.2 moles of that, so 7.2 divided by 6 gives us 1.2 moles. And then we do the same for hydrogen, so we've got 12 moles of that, and we're going to divide that by 6, which gives us 2 moles. Okay, now the next thing, so it says it was allowed to reach equilibrium at a constant temperature and without changing the total gas volume. So we don't really need that to answer this question. We've used the information in this bullet point, and then we've got the value for Kc. So if we refer back to that Kc expression, which we've just written at the top of the page, but I'll remind you of it here. And we've got the value for Kc, so we've got this, and we've got the value for N2 and the value for H2, and what we need is the NH3. So now we're going to rearrange this expression. So if we take these terms up to the top, we've got Kc times the concentration of N2 times the concentration of H2 cubed, and that would equal NH3 squared. So if we square root the whole of this, then that's going to give us the concentration of NH3. If you put your numbers in, so 8 times 10 to the minus 2, which comes from the question up here, times 1.2, which comes from here, times 2 cubed, and 2 came from there, square root all of that, and that gives us 0.876 moles. Okay, now remember we went from 6 decimeters down to per decimeter by doing this. Now it asks us how much ammonia is present in the equilibrium mixture. Well, that is of course still in 6 decimeters, so the final step will be to multiply back up. And that gives us a final answer of 5.26, which is what should go here. Running through the marks on this question then, we need to have both of these numbers for the first mark. The next mark comes for this rearranged equation, either written like this or with your substituted numbers. Third mark is for your answer here, and the fourth mark is for your final answer. Many people miss this final mark because they forget to multiply back up by 6. Other common errors are to forget to divide by 6 in the first step, but of course you would then get errors carried forward from that. Question 5 part C continues with the theme of equilibrium. We're being asked to talk about how equilibrium will change when we change some of the conditions. Okay, so if we look at what we're changing, we are doubling the pressure and keeping everything else the same. C part 1 asks us to explain in terms of Le Chatelier's principle why the equilibrium yield of ammonia increased. Now this is a synoptic question because remember Le Chatelier is from F322. So what we need to say is that equilibrium shifts to the right, and then we need to say because there are fewer gaseous moles on the right hand side. Okay, so again, synoptic, nice question, 1 mark for each of those statements. Underneath that we've got explaining in terms of Kc, so this is bringing in your A2 knowledge. We're going to say that Kc is unchanged by pressure. Okay, you cannot get that one wrong, because if you say anything at all about Kc being changed by pressure, you get 0 marks in this part of the question. So you must say that one. Now we're going to explain it. So changing pressure means that the system is no longer in equilibrium. Okay, on the mark scheme, also an alternative answer to this is to say that increasing pressure affects the bottom of the Kc expression more than the top. Now, if you want to know more about that, go and find the video that we'll have on this Kc expression and pressure effects in it. In this mark scheme, it's not so bothered about you saying that. It's quite happy for you to just say that the system's no longer in equilibrium, so we'll leave it at that. And the final point is to say that the top of the Kc expression will increase, i.e. more ammonia, and the bottom will decrease, so less of the reactants, until Kc is reached. So 3 marks in this question. 1 for saying Kc is unchanged by pressure. If you omitted that part of the answer, then you could still be credited for the second 2 points, but if you said anything at all about Kc being changed by pressure, then you got 0 for the rest of it. Once you got past that point, it was 1 for each of these statements. Moving on to part D, we've got for the industrial manufacture of ammonia, nitrogen and hydrogen gases are required in large quantities from readily available resources. Various methods have been developed to obtain hydrogen gas for this process. Much of the hydrogen is obtained by reacting together natural gas, methane, that goes on the left of our equation, and steam, so water. Construct an equation, so we're already halfway there. And what we're making is hydrogen, and then we need to think what else we might make. So If I was to look at this question, then I would say I could make from this 3 lots of hydrogen, and then I'd be left with some carbon monoxide. Take a quick look at the mark scheme. There were quite a few allowed answers on this one, so the easiest one was what I went for there. But again, you've got quite a few alternative answers, so do have a look through those answers on the mark scheme if you have given something different to what I've said. Then we've got natural gas is a fossil fuel, and the annual production of ammonia accounts for about 2% of all methane consumption. In the future, as fossil fuels become more depleted, the use of methane for ammonia production may become too expensive. Suggest another process that might be used in the future to obtain hydrogen gas for the Haber process. And the mark scheme says on this one, electrolysis of water. Which would be the following equation, so water breaking down into H2 and a half O2, which is the reverse of what's going on in a hydrogen fuel cell. Part E is the entropy question in this paper. And looking at this question, we're sticking with the Haber process. We've been given some S values, so some entropy values for the reactants and products in this equation. And when you see S values, you should be thinking of using delta S equals SP minus SR. So if we look at the calculation, we're going to do delta S. Products in this are ammonia, and we've got 2 of them, so 2 times 192. Take away reactants, so we've got nitrogen, 191, and 3 lots of hydrogen. And that gives us an answer of minus 200, and that is in joules per Kelvin per mole. Now that's important, but the units don't get you a mark at this stage. Remember that when this goes into the delta G equation, we're going to divide that by 1000, and it will be 0.2 kilojoules per Kelvin per mole. Okay, so that's very important that you remember to divide that delta S by 1000. Now the next thing we're going to look at is when we see the word feasible in an entropy question, we should be writing down the delta G, the Gibbs function equation. Okay, it's really important in an entropy question that you always write this equation out, because generally in the mark scheme there is a mark just for writing that down. So if you got to this question, maybe you were short on time, or maybe you looked at it and you weren't quite sure what to do, as long as you recognise it's an entropy question and you see the word feasible, at the very least write down this equation, because it will be worth a mark. Now the next thing is to just put the numbers into the Gibbs function equation. So delta H is up here, it's minus 92. Okay, so that's in kilojoules per mole, which is why we needed the entropy to be in kilojoules. We've got to convert the temperature because it's in degrees Celsius here, and we need it to be in Kelvin for this equation. Remember, to convert from degrees Celsius into Kelvin, we're adding 273, but 25 degrees is standard temperature, which we should know is 298. And we're going to times that by the 0.2 that we worked out here. When we put that into our calculator, we should get an answer of minus 32.4 kilojoules per mole. Going through the marks in this question then, we get 1 for the delta S calculation, 1 for the correct answer, 1 for writing out the delta G equation, and 1 for the final answer. On this one, however, the units are required. You must have kilojoules per mole with your final answer. And the other one is for recognising that we need to use the temperature in Kelvin and using the figure of 298 in your calculation. Moving on down to part 2. So if we think about the delta G expression that we've just been using, we know that delta H is negative and we know that delta S is negative because we've just worked that out above. So we want delta G to be negative for the reaction to be feasible. And what happens is, when we increase the temperature, so we're increasing T, then the value of T delta S becomes more negative. If the value of T delta S, so this term here, if this term is more negative than delta H, then overall the answer will be positive. Again, I would suggest that you go and watch the video tutorial on using this equation if you're struggling with this bit. So we're going to say that at high temperature, the value of T delta S, apologies I don't have delta sign, becomes more negative than delta H. Okay, so that's our first one. So at high temperatures, the value of T delta S becomes more negative than delta H. Now the next statement I'm going to say is that delta H minus T delta S becomes positive at high temperatures. Okay, so what we're saying there is that when we increase T, so at high temperatures, the value of T delta S becomes more negative than delta H. When we do the calculation, so delta H minus T delta S becomes positive at high temperatures, i.e. Gibbs is positive and the reaction is not feasible. Now the bottom question, very nice question tagged on to the end. So as I always say, don't ever get put off by a question because there's a nice one marker hiding in it somewhere, and make sure you get that one. So suggest why a temperature of 400 to 500 degrees is used for ammonia production despite the reaction being feasible at room temperature, and that is because the activation energy is too high or the rate is too slow at room temperature. Okay, so nice straightforward question to finish this 22 mark equilibrium and entropy question. Question 6 is a mixture of transition elements and electrode potentials. We're starting this question with a fairly straightforward electron configuration question. It's testing your knowledge of the periodic table, so if you use your periodic table you'll find that chromium has an atomic number of 24, and it's testing your AS knowledge of electron configuration. So if we start completing that now, it follows as you would normally expect until we get to the 4s and the 3d. Okay, now some people will write these as 3d and 4s. It doesn't matter which way around you write them, as long as you remember to fill them in the correct order. So 4s fills first and 3d fills second. Now if you did this for most other elements you would be correct. However, chromium is one of the exceptions that you learn about in A2. And you should know that instead of existing as 4s2 3d4, it's more energetically stable for it to exist as 4s1 3d5, giving it two half-full subshells. Then we go to the Cr3 plus ion, and again, fairly straightforward to start off with, all the way up to that 4s electron. Now remember, when transition elements form ions, it's the 4s electrons that go first. So we're going to lose that 4s electron, that's gone. And then we're going to need to lose another 2 from the 3d, so that gives us 3d3. In part B, we're asked to balance some half equations.
The first one's fairly straightforward, so if we look, we've got one zinc on the left and one zinc on the right, so we just need to balance the electrons. If there's a 2 plus charge here, we need to balance that out with 2 minuses, so all we need to do there is add 2 electrons. The chromium dichromate half equation, slightly more difficult. So we start off with the chromium, there's 1 on the left, so that means we need 2 over here. On the left we've got 7 oxygens, which means that we're going to need 7 waters on this side. We've now got 14 hydrogens on the right, so we'll need to put 14 in there. And then finally we'll deal with the charge. So we've got the overall net charge on the right hand side here is plus 4 because we've got 2 times 2 plus. And the overall charge on this side, so we've got minus 2 add 14, lots of pluses. So we've got an overall charge of plus 12, which means that we need to balance that to make plus 4. So that means that we need 8 electrons. Okay, so just run through that again. On this side we've got 2 times 2 plus, giving us a charge overall of plus 4 on the right hand side. On the left hand side we've got a 2 minus charge and 14 positive charges, giving us an overall of plus 12. We need to make both sides equal, and we can only add electrons, so we're going to need to add them to the left, which we can see in the question anyway. So to bring 12 down to 4, we need to add 8 electrons. Okay, so that's the first 2 marks in this question, because it's going to be 1 for each half equation. And then it says construct an overall equation for this reaction. So if we look now, we've got 8 electrons in this bottom half equation and 2 in the top, so we're going to need to times the top by 4 to make them equal. And then we're just going to add them together, so we're going to have 4 lots of zinc plus that dichromate and those hydrogen ions. Remember, the electrons will cancel, so we won't even put them in. And on the right hand side we're going to have 4 lots of zinc, 2 plus, and the 2 lots of chromium and 7 waters. And that should be your 3 marks. So 1 for balancing each half equation and 1 for your overall equation. Moving on to part C. So we've got aqueous solutions of chromium 3 plus ions contain ruby coloured chromium hexaaqua ions. If an excess of concentrated ammonia is added, the solution changes to a violet colour as the hexaamine chromium 3 complex ion forms. So what we've got going on here is we've got water ligands being replaced by amine or ammonia ligands. So that should tell us that this is a ligand substitution reaction. And the equation, so we're starting off with the chromium with 6 water ligands, and we're ending up with chromium, and it says hexa, so that's 6, and it says amine, so 6 ammonia ligands. Okay, remember ammonia is a neutral ligand, just the same as water is, so the charge is going to be the same. So on the left we're going to need to add in 6 ammonias to take the place of the waters, and on the right we're going to have the 6 water ligands that have been kicked out of the complex. If you are following this through with the mark scheme, you will see that it's 1 mark for the left hand side of the equation and 1 mark for the right. So you really do need to attempt equations like this, because it may be that you get something wrong, but you could well pick up 1 of those marks. Question D is a fairly standard question for an F325 paper. We're given a little bit of information about a complex, and we're given this structure of an unfamiliar bidentate ligand. So if you've not watched the video about drawing bidentate complexes, it may be worth a watch to make sure that you can draw them. However, for now I'm going to run through the questions that were given. So before I look at the questions, again, it's quite useful to preempt what the examiner is going to ask you. So looking at this structure, we're going to look for where the lone pairs of electrons are that it would use to form those coordinate bonds with the central metal ion. So we've got some lone pairs on these oxygens and also one on the nitrogen. Now thinking about how this is going to act as a bidentate ligand, remember we're looking for that shape of kind of a bridge with two ligands on it. Now you could go for between the two oxygens. I'm going to go for the likelihood of being this area that we're forming the bidentate complex in. And I'll come back to that in one of the questions below. Now the first question asks us to explain what is meant by the term ligand, so this should be a very straightforward definition that you've learnt, because 10% of your paper roughly will be on definitions, so you cannot afford to not know them. So ligand, species with a lone pair of electrons that it can donate to a central metal ion to form a coordinate bond. Okay, so I've said both of the things that are said in the mark scheme there, but I really do think it's worthwhile just learning that definition as is, and then you've covered all bases. Now the second part of this question asks us to explain how the picolinate ion can act as a bidentate ligand, and bidentate is in bold, so that means that's the word we need to explain. So picolinate has two lone pairs of electrons that it can donate to form two coordinate bonds. These lone pairs are located on the oxygen and nitrogen. Now, I've gone for the oxygen and nitrogen. If you are looking at the mark scheme, you may be questioning that, because the mark scheme does say lone pairs on two oxygen atoms, but if you look over here, you can see that lone pair on oxygen and nitrogen is an allowed answer. Now the reason I've gone for them is because if you do go and look up the structure of chromium picolinate, it is the nitrogen and the oxygen that are used to form the coordinate bonds. So either way, if you do go for the two oxygens, you must state that it is the two oxygens, because it can't use the lone pairs from one oxygen to form two coordinate bonds. So you must convey this idea that they are in two separate places on two different atoms. Carrying on down, we've got why does chromium picolinate exist as a mixture of stereoisomers? So we are going to write it can form two optical isomers which are non-superimposable mirror images of each other. Okay, and that's going to be our first mark. And then it says draw diagrams of the stereoisomers. So mark scheme's fairly nice in this respect, because it allows you to use the shorthand notation for the two optical isomers. So if we look at this, we've got 3 lots of a bidentate ligand, so 3 times 2 is 6, coordination number of 6, the shape is octahedral. So if we draw that shape around these two chromiums, remember if we're drawing stereoisomers we have to draw in 3D. So we'll put all the bonds around it. I've lost my mouse cursor now. I'll try that one again. So chromium with an octahedral shape around it. And the mark scheme will allow any attempt at drawing these bidentate ligands. So I'm going to draw them like that. You could have gone for headphones if you'd have wanted to, like this. Okay, but I'm going to keep mine the same, just use L. And then we draw the mirror image over on this side. And we get 1 mark for each stereoisomer and 1 mark for the explanation. Just very quickly, I'm just going to show you what these two stereoisomers would have looked like if I'd have attempted to draw the whole thing on there, because in an exam situation I think that's what I'd have been likely to do, because the question doesn't say that you can use an abbreviated version of it. So I'm just going to draw that ligand there again. Okay, so that was the picolinate ligand, drawn very badly. And we start off by drawing the chromium with its octahedral shape again. Remember, I'm using the nitrogen and the oxygen, so I'm going to go with a nitrogen there and an oxygen there. Then I follow the bridge around like that. Okay, so from the oxygen I go to a carbon. Then I've got a bridge across there. Then I'm going to fill in the rest of the ring structure with the double bonds on it. And then the carbon's got a double bond oxygen coming off it. And then similarly, if I go down to this one, okay, so fill in the bridge. And put the double bond O on. And the last one, there's the bridge. Okay, so it took me quite a lot longer, but if I was doing this in an exam, and with the question not telling me that I can use any abbreviation for that bidentate complex, this is probably what I would have drawn. And then to draw the mirror image, I'd have done the same thing again. And I'm going to start with this one here. So I've got a nitrogen there and an oxygen there. And rather than trying to draw the mirror image directly, I'm going to just use the positions of the atoms and then work it from there. So if I'll go down to this ligand, I've got a nitrogen on this bond coming out and an oxygen there. So again, just fill the rest of the ligand in around it. And then looking up at the top two, so the nitrogen's on this one going back and the oxygen's there. Okay, so they are the two mirror images. Not very easy to draw, but again, not impossible either. So if you do find yourself in that situation and you're not sure what to draw, you could always attempt them. You could maybe draw the other one at the side. Although I'm not sure how that would be viewed if you got this right and those wrong. It's one of those, if you don't think you can cope with drawing the whole thing and getting it right, always go for this kind of headphones look instead when you're drawing bidentate ligands. If you think you can get it right and the exam question doesn't give you any indication on whether you can use an abbreviation or not, then try drawing it. The final part of this question is quite synoptic in nature. We're given some empirical formula data and we've also got a mass down here which would suggest a moles calculation. What we're being asked to do is to work out the identities of compounds A, B and C. It's a long answer question and we have as usual been given bullet points which tell us how to structure the answer. So we're going to start with the first one, which asks us to work out the empirical formula of compound A. So empirical formula is a calculation that you will have learnt in AS F321, and there is no difference between then and now in terms of this calculation. So the first step is to divide the percentage of each of those elements by its atomic mass.
And once we have those numbers, the next step is to ratio them by dividing by the smallest number, which is this one here. So this will be number 1. So you can see that I've ratioed the numbers. I do always find it useful when doing empirical formula at this stage to do all the numbers to one decimal place, because it makes it very obvious when you get fractions such as this one, which will of course need to be multiplied out because you can't have half of an oxygen atom. So we're going to need to times all these numbers by 2, which gives us 2 nitrogens, 4 hydrogens, 2 chromiums and 7 oxygens. So the empirical formula is N2H8Cr2O7, and just as in F321, it's very important that you write out the final formula like this, because if you look at the marks, we get 1 for the calculation and 1 for actually writing out the final formula. Okay, so that's the first bullet point dealt with. Now if we look at the second one, it says deduce the ions that make up the ionic compound A. So here's where we're going to have to employ a little bit of our knowledge from AS and A2. So if we look at this formula, and the thing that stands out here is the dichromate ion, okay, which you will have first met in oxidation of alcohols in AS, but again you'll have met it this year in transition elements and in electrode potentials. And then if we look at what's left, now OCR are not going to expect you to make up ions that you've never met before, so they'll be relying on you to think about those ions that you've had to learn over the 2 years, so like sulfate, nitrate, carbonate, ammonium. And if we look at this N2H8, we can make NH4 plus 2 lots of that from what we've got in that empirical formula. And again, following the mark scheme, we get 1 mark for each of those ions. So that would be the second bullet point dealt with. Then it says identify substances B and C. So if we look at B, it says it's a green oxide of chromium with a molar mass of 152. So let's deal with that here. So we know that the MR of this compound is 152. We know that chromium has a mass of 52 and oxygen is 16. So the way that I would attempt this is I would look at it and say, right, if I use 2 chromiums, then that would give me a mass of 104. 152 take away 104 gives me 48. And then I'd think about how many oxygens I can make from that. So 48 divided by 16 gives me 3 oxygens, which means that the formula of compound B is Cr2O3. That is mark number 5. Identifying compound C, slightly more complicated. So things that we know about C, we know that it is a gas. Okay, so it's a gas at room temperature and pressure. And then it says each cubic decimeter. Now it's very easy to miss this, but that is of course a volume of 1 decimeter cubed, which means that if we are looking at a gas, then we can use N equals V over 24. So I'll put the calculation down here. So number of moles equals V over 24 equals 1 decimeter over 24. Gives us an answer of 0.0416 recurring. Now the thing that I would do next is, if you look in the question, we've got a mass of 1.17 grams. So if I rearrange N equals M over MR to give me MR equals M over N, then I can put my numbers into that. So 1.17 divided by 0.416 recurring, and that gives me 28.08 as the MR. Okay, so MR of C is 28.08. You will notice that if you look at the mark scheme for this question, the mark scheme does just say 1.17 times 24. Now I've had quite a few students ask me why the mark scheme says that, and the reason is that what you are doing is that you are doing n equals V over 24, and then you're taking this number, so you've got 1 divided by 24, and then you're doing m over n because this number gives you n. So we've got 1.17 divided by 1 over 24, and without going into all the maths of rearranging all of this, basically what that works out to doing is 1.17 times by 24. Now remember, the mark scheme is written to make it easy for examiners to look for marks. So all they're looking for is your final answer of 28.08. Now the way that we get to it in this question is by working through logically the moles calculations that we've used all the way through from AS up until now. Now I would argue to stick with this, because to just worry about where that 24 in the mark scheme comes from is not that productive. Okay, so stick with the fact, look at your question like you would normally do. You've got a volume and you know that it's a gas, you're doing V over 24. Once you've got your number of moles, you've got mass, find the MR. Stick with the steps that you've learnt for the past 2 years and it will get you to the right answer. So don't get too tied up with where this 24 in the mark schemes come from, and stick with what you know to do. You can still get to the same answer. Now the next thing to do is to identify the gas C. So we're looking for a gas with an MR of 28. Okay, compound C is formed from heating compound A. So if we look at what compound A is made out of, so we'll remind ourselves it's up here, it's N2H8Cr2O7. Chromium is not going to form part of a gas, so we've got basically the choices of nitrogen, hydrogen and oxygen atoms. Okay, so it's time to employ a little bit of common sense again. It couldn't be O2 because O2 would add up to 32. It couldn't be H2 because that would add up to 2. Water, H2O, is 18. So the most logical choice here is N2, which of course 2 lots of 14 do add up to 28. And identifying C as N2 gets us mark number 7. And the final part of this question, so we cross that one off, final bullet point says write an equation for the decomposition of compound A by heat. Okay, so compound A is N2H8Cr2O7. You will notice on the mark scheme that they have turned that into NH4 2Cr2O7, and that's because we did identify the ions earlier. But in the equation, either of these is allowed, so I'm going to stick with this one because I would guess that this is what most people would go for when answering this question. And we are going to decompose that, so it's thermal decomposition, we're not reacting it with anything. I'm going to decompose it to make compounds B, which was Cr2O3, and compound C, which is N2. And then if we look at what we've not used, so we've used the 2 chromiums, we've used 3 of the oxygens, so that's 4 left. We've used the 2 nitrogens and we've got 8 hydrogens. 8 hydrogens and 4 oxygens are going to end up making 4 lots of water. And that is the final mark in this question. Question 7 brings us back to half equations, and we're introducing redox titrations in this question. What we've been given is a half equation and a whole equation, so an overall equation, and we're asked to find the simplest whole number half equation for the oxidation of hydrogen peroxide under these conditions. So we're being asked to find the missing half equation that made this whole equation. So what I need to do is subtract this half equation from this overall equation. Now there's various ways of doing this, but I'm going to show you the way that I would attempt this question. So my first thing is, ignoring any stoichiometric numbers, I'm just going to cancel any species that are in this half equation with those in the overall equation. Okay, and then I'm going to write out what I'm left with. So I've got 5H2O2 makes 5O2. Obviously then I can get rid of those 5's because we're going for the simplest whole number ratio, so the 5's will disappear. Next thing I'm going to do is I'm going to balance this half equation. So again, if you've not watched the tutorial on balancing half equations, go and do that if you're not quite getting what I'm going through now. So if we look at either of these equations, we can see that they are in fact in acidic conditions, because both of these equations contain H plus ions. So we're going to balance this half equation in acidic conditions. So in acidic conditions we balance hydrogen with H plus, oxygen with water, and charge with electrons. Okay, so we've got two hydrogens here, which means we need 2H plus on this side. Oxygens are balanced because we've got 2 on the left and 2 on the right. And then charge with electrons, so this left hand side here is neutral. The right hand side has 2 positives, so we're going to need 2 electrons to balance that out. And this is our missing half equation. The final question on this paper is a titration question. A2 titrations tend to be a couple of steps more complicated than AS, because in AS you would probably have started around about here and you'd have had a volume and a concentration leading you into N equals CV over 1000. In A2 we've got added complications from things like dilutions, as in this question, which mean that when we're looking through the question we can see quite a few different volumes, and it can get quite confusing as to what you're actually having to do. So we've got another volume there as well. Now, I'll walk you through the way that I would attempt this question. I tend to form a mental picture of what's happening in the description of the question. It won't work for everybody, and everybody's mental picture will be slightly different, but I'll show you how I will do it, and then you can hopefully from that go away and understand the mark scheme. So, reading through this question, student diluted 25 centimeters cubed of a solution of hydrogen peroxide with water. Okay, so here is my original H2O2 solution. Okay, so that's the original undiluted hydrogen peroxide solution, and I'm taking 25 centimeters cubed of that, and I am transferring it into this volumetric flask. So in my volumetric flask I've got the 25 centimeter cubed aqualot, and then I've made that up to the mark with water. Okay, so now I've got a diluted solution which has a volume of 250 centimeters cubed. Then I'm going to take 25 centimeters cubed of that, and I'm going to put it into this conical flask, and I'm going to titrate it with potassium permanganate. Okay, so in the conical flask I've got some of that diluted solution. Now I can start working my way back through all those volumes and concentrations in the question. So I'm going to start at the end, because it's always where you start at the end and then work backwards, because what we need to know is the concentration of this in grams per decimeter. Okay, so again, bullet points tell us what we need to do. So as I've just said, the first one says calculate the concentration in grams per decimeter cubed of the undiluted hydrogen peroxide solution over here. So we'll start with the potassium permanganate, and we can see that the permanganate is here. The volume of potassium permanganate was 23.45, so we can put that in up here. And the concentration is here, so the concentration equals 0.02 moles per decimeter. Now we can step into the moles calculation. So if we've got V and C, then we're going to be doing N equals CV over 1000. Substitute the numbers in, so 23.45 times 0.02 over 1000 and that gives us 4.69 times 10 to the minus 4 moles of KMnO4. Okay, so if you are following the mark scheme, you'll see that that number is mark number 1. Next, from this, we're going to need to get to moles of H2O2 in the 25 centimeters cubed portion that's in this conical flask, and for that we're going to need the molar ratio. So we look back on the previous page where we've got the balanced equation here, and we can see that the ratio between the manganate and the peroxide is 2 to 5. So if we've got moles of manganate, we're going to divide by 2 and times by 5 to get moles of peroxide. So if we go back over here, so we're going to do 4.69 times 10 to the minus 4 divided by 2 times by 5, and that gives us 1.1725 times 10 to the minus 3 moles of H2O2 in this 25 centimeters cubed, and that number's the second mark in the mark scheme. Next thing we're going to do is to go back from, if we know the moles in this 25 centimeters cubed portion, how many were in the 250? So to get from 25 to 250, we're going to multiply by 10. So moles of H2O2 in 250 centimeters cubed equals 1.1725 times 10 to the minus 3 times by 10 gives us 1.1725 times 10 to the minus 2. That's mark number 3 in the mark scheme. Next step is where it gets slightly complicated. So what you've got to think about now is, if I know how many moles are in this 250 centimeter cubed volumetric flask, then actually that's the number of moles that are in this 25 centimeter cubed that I transferred in from this solution. Okay, so just run through that again. We've got the moles of permanganate, we've ratioed to get the moles of hydrogen peroxide in the 25 centimeter cubed in the conical flask. We've multiplied by 10 to get back to how many moles were in this 250 centimeter cubed volumetric flask. And now we're going to get back to the original undiluted solution. So in this volumetric flask there are 25 centimeters cubed of that original solution. So now we're going to say V equals 25, N equals 1.1725 times 10 to the minus 2. And so we're going to work out concentration. So C equals N times 1000 over V, and that gives us 1.1725 times 10 to the minus 2 times 1000 divided by 25, and that gives us 0.469. No marks for this yet at this point. Now lots of people get very confused with the mark scheme because they're asking where the number 40 comes from in the mark scheme, and the answer to that is from this bit here. Okay, because 1000 divided by 25 is 40. So we're doing 1.1725 times 10 to the minus 2 times by 40. Now, the only reason this is all condensed into one thing in the mark scheme is to make it easier for examiners to follow through and mark. To work this out in an exam, you're going to need to be able to do it step by step, which is what we're doing here. Okay, so the first step is to find the concentration of the solution, and that is of course in moles per decimeter. If we look back at the bullet point up here, it says it wants the concentration in grams per decimeter. Okay, so if we're in moles per decimeter, to get to grams per decimeter, we're going to need to times by the MR. So concentration in grams per decimeter equals 1.1725, apologies, wrong number, equals 0.469 times by 34, which is the MR of H2O2, and that gives us 15.946 grams per decimetre, and that's the number you will find on the mark scheme. Okay, so looking at the mark scheme again, you'll see 1.1725 times 10 to the minus 2 times by 40, which is where this comes in, and then times by 34, which is the MR, and that gives this 15.946 grams per decimetre. So again, all I've done is broken it down into the steps that you'd be more likely to take if you were working through this in an exam situation. If we go up to those bullet points, we can now tick off that first one. And the next one's asking us what volume of oxygen gas measured at room temperature and pressure would be produced during this titration. Okay, so we're looking at the titration again. So if we're going bullet point 2. And we'll just remind ourselves that the moles of manganate were, and that's up here, 4.69 times 10 to the minus 4. Now we want to know the moles of oxygen. So for that we're going to need to go back to the equation again over here. Let's just get rid of this. And we're going to need to look at the ratio again. So this time we're going from manganate to oxygen. And again the ratio is 2 to 5. So we're going to use the ratio to calculate the moles of oxygen. So we're going to do 4.69 times 10 to the minus 4 divided by 2 times by 5 gives us 1.1725 times 10 to the minus 3 moles of O2. So that's mark number 5. And then it's asking us for the volume of oxygen, so we're going to do V equals N times 24. So we've got 1.1725 times 10 to the minus 3 times by 24, and that gives us 0.0281 decimeters cubed. Now on the mark scheme it does say that you have to have both the number and the unit stated, because you could also have used V equals N times 24,000 and you would have ended up with an answer of 28.1 centimeters cubed. So you've got to state which one you're using by showing your units, because either one of these answers would get you that final mark. And that's the end of the paper.